Welcome back to Stack Lessons. 20 questions today, focused on AI search endpoint sizing, RAG chunking architecture, and Unity Catalog governance. Quick reminder of the format. Question read aloud, 10-second countdown, answer revealed, then the explanation. Let's see how you do. Ready. Question 1. Convert the story into selection criteria. A generative AI engineer at Fernbridge Insurance is preparing to deploy a production LLM application that processes insurance claim documents for 4,000 agents simultaneously during peak hours. The team requires consistent response times and has a fixed monthly operations budget. Which model serving configuration should they use? Select one. Review the answer choices on screen. The correct answer is option C. Dedicated capacity is the only guarantee under sustained load. Provisioned throughput endpoints allocate dedicated inference capacity expressed as model units, guaranteeing consistent latency under sustained high concurrency load and generating a predictable fixed monthly cost. Databricks explicitly recommends provisioned throughput for all production workloads with performance requirements. Pay-per-token endpoints are recommended for development and exploration phases where usage is variable and low. They lack dedicated resources and cannot guarantee latency under consistently heavy concurrent load. A serverless endpoint that scales to zero introduces cold start delays when peak demand resumes and cannot maintain response consistency for 4,000 simultaneous agents. External model endpoints through AI Gateway introduce additional network round trips and depend on third-party capacity, which cannot meet the fixed budget or guarantee performance requirements. Ready. Question 2. Separate fact from assumption. A generative AI engineer at a Datum Corp wants to ensure that all ML feature tables and registered model versions share a unified discovery namespace, but data scientists can trace which feature tables were used to train each model version, and that access to feature tables containing customer PII is governed through role-based permissions. Which platform capability satisfies all three requirements? Select one. Review the answer choices on screen. The correct answer is option A. Three distinct requirements. Only one platform satisfies all. Unity Catalog provides the unified governance layer that satisfies all three requirements. A three-level namespace, catalog.schema.object, for consistent discovery, automatic lineage tracking that links feature tables to the model versions trained on them, and permission management at the catalog, schema, or table level to restrict access to sensitive data. MLflow autologging captures training metrics and parameters, but does not enforce access controls or produce governance-level lineage for feature table usage. LangChain Spark Declarative Pipelines manages pipeline lineage for ETL workflows and is not designed for ML feature or model version governance. Publishing feature tables to DBFS bypasses Unity Catalog governance entirely, making centralized access control and cross-asset lineage unavailable. Let us switch gears. Question 3, wording first, memory second. A generative AI engineer at Ashford Analytics is registering a trained fraud detection model to Unity Catalog using MLflow. The organization uses a catalog named risk_ops and a schema named ML_models. Which model name should be passed as the name argument to lflow.register_model to correctly register the model in Unity Catalog? Select one. Review the answer choices on screen. The correct answer is option A. Three levels, .delimited, that is the entire rule. Unity Catalog uses a three-level .delimited namespace for every managed object, including registered models. The required format is catalog.schema.model_name, making risk_ops.ml_models.fraud_detector the correct argument. Forward slashes are not valid namespace separators in Unity catalog syntax and will cause the registration call to fail with an error. Double colons are equally invalid as namespace delimiters for Unity catalog model names and produce the same failure. Providing only the model name without catalog and schema qualifiers either resolves to the legacy workspace level registry or fails when MLflow is configured with the Databricks UC registry URI, which is the default in MLflow 3. Keep your focus here. Question 4. Start with what the user needs. A generative AI engineer is building a RAG system over multi-hundred-page technical manuals. Small chunks improve retrieval precision but lack enough surrounding context for the LLM to generate complete answers, while large chunks degrade retrieval accuracy. Which retrieval strategy resolves this tension most directly? Select one. Review the answer choices on screen. The correct answer is option B. Decouple the search unit from the context unit. Parent-child retrieval decouples the granularity used for search from the granularity used for generation. Small 512 token child chunks are indexed and retrieved with high precision because they closely match the specificity of most queries. Once the relevant child chunk is identified, the larger 2048 token parent segment that contains it is passed to the LLM, giving the model enough surrounding context to generate a complete and coherent answer. Semantic chunking produces semantically coherent segments, but does not address the core tension because each chunk still serves double duty as both the retrieval unit and the generation context unit. A single 1024 token chunk attempts a compromise, but neither maximizes retrieval precision nor maximizes the context richness delivered to the LLM. Using a re-ranker with 256 token chunks scores existing retrieved chunks differently, but does not expand the amount of context actually passed to the LLM for generation. Keep your focus here. Question 5. Verify the constraint first. A generative AI engineer at Crestwood Analytics is building a semantic search system over a product catalog that has grown to 1.5 billion item descriptions. The team's primary concerns are storage cost and indexing speed. Query latency under 500 milliseconds is acceptable. Which AI search endpoint type should they choose? Select one. Review the answer choices on screen. The correct answer is option A. The 500 milliseconds budget is the unlock. Read it carefully. Storage-optimized endpoints are purpose-built for very large vector corpora exceeding 1 billion vectors. They deliver 10 to 20 times faster indexing throughput and lower per-vector storage costs compared to standard endpoints, which are capped at approximately 320 million vectors at 768 dimensions. The trade-off is approximately a 250 millisecond increase in query latency, but total latency remains within the team's 500 millisecond budget. Standard endpoints cannot hold 1.5 billion vectors, and the 50 index maximum per endpoint represents a count of indexes, not a mechanism for scaling beyond the vector capacity limit. Storage-optimized endpoints do add approximately 250 milliseconds of latency, but this does not push total query time beyond 500 milliseconds under normal operating conditions, making the rejection in the fourth option incorrect. Let's slow down here. Picking the right endpoint type at billion vector scale is exactly what this exam tests. Imagine your product catalog just crossed 1.5 billion descriptions. Your standard vector index maxes out around 320 million vectors. You're already 5 times past that. So option D's idea of sharding across 50 indexes won't save you. That's a count limit, not a capacity trick. The storage-optimized endpoint is built for exactly this scale. Yes, it adds about 250 milliseconds to each query, but your team's budget is 500 milliseconds. You're still in the clear. Faster indexing and lower cost seal the deal. The exam tests whether you know the capacity ceiling, not just the latency number. 3 patterns surface in the first 5. Provision capacity when SLAs are non-negotiable. Switch to storage optimized when a corpus exceeds 1 billion vectors, and bet on Unity Catalog whenever a question lists multiple governance requirements. Keep your focus here. Let's get into question 6. A generative AI engineer at Cascade Research is building a scientific literature search system that will index over 2 billion research paper embeddings at 768 dimensions. They need to query this index in production. Which AI search endpoint type should they provision? Select one. Review the answer choices on screen. The correct answer is option D. Standard endpoints simply cannot hold 2 billion vectors. Storage-optimized endpoints are specifically designed for corpora exceeding 1 billion vectors, making them the correct choice when the vector dataset surpasses what a standard endpoint can accommodate. Standard endpoints support approximately 320 million vectors at 768 dimensions, far below the 2 billion vector requirement. No amount of configuration on a standard endpoint resolves this capacity ceiling. Sharding across multiple workspaces is not a supported native AI search topology. Delta Sync versus Direct Access describes how embeddings are managed and updated, not the endpoint's vector capacity. Both index types can be hosted on storage-optimized endpoints. Okay, question 7. Look for the answer that fully satisfies it. A generative AI engineer is preparing a delta table to back a Databricks AI Search Delta Sync index. After loading source data into a Spark data frame, the engineer finds the primary key column is named _i.d. The engineer attempts to create the Delta Sync index and receives an error. What is the root cause and the correct remediation? Select one. Review the answer choices on screen. The correct answer is option A. The column name is the problem, not its data type. The column name _i.d is reserved within Databricks AI Search and cannot be used as a column name in the backing delta table. Attempting to create a delta sync index on a table containing a column named _i.d raises an error, and the correct remediation is to rename that column before creating the index. Change data feed must also be enabled on the source delta table for a delta sync index to function, but that is a separate prerequisite that produces a different error and is unrelated to the reserved name conflict. Casting the column to long type does not resolve a reserved name violation. The issue is the column name itself, not its data type. AI search requires the engineer to specify a primary key column. It does not auto-generate identifiers, so dropping the column would make it impossible to uniquely identify individual records in the index. Okay, question 8. Ignore details that do not change the decision. A generative AI engineer at a Datum corporation is designing an employee benefits assistant. The source data includes structured eligibility rules stored in SQL tables and unstructured policy explanations stored in PDF documents. The engineer needs a retrieval strategy that handles both data types accurately without losing the precision of the structured data. Which architecture should they implement? Select one. Review the answer choices on screen. The correct answer is option B. Structured facts need SQL precision. Documents need semantic search. Structured relational data and unstructured document data require fundamentally different retrieval mechanisms to serve their respective strengths. SQL tables contain precise, queryable facts, such as eligibility thresholds and coverage tiers, that are best retrieved with SQL queries capable of filtering and aggregating with full relational precision. PDFs contain narrative policy explanations that benefit from semantic similarity search in AI search, Routing each query to the appropriate mechanism delivers accurate results from both sources. Embedding SQL table rows as text chunks loses the precision and expressiveness of structured querying, and introduces fuzzy semantic matching in contexts where exact filtering is required. Flattening all data into a single text file destroys the relational structure of SQL tables entirely, producing incoherent chunks that merge precise facts with narrative prose. Storing tables as CSV files in a volume and parsing them line by line is operationally complex, loses the query optimization of a proper database, and provides neither the efficiency of SQL nor the semantic richness of vector search. Here we go. Question 9. This is a two-step filter. A generative AI engineer at Belcore Systems has enabled inference tables on a model serving endpoint. They need to write SQL queries that 1. Calculate the average processing duration per request, 2. Identify all requests that returned a server-side error, and 3. Attribute usage to the specific client application that sent each request. Which three columns from the inference table schema directly support these three requirements? Select 3. Review the answer choices on screen. The correct answers are Option A, Option C, and Option E. 3 requirements, 3 columns, 2 decoys look entirely plausible. Execution_time_ms records the processing duration of each individual request in milliseconds, making it the correct column for calculating average serving time. Status_code captures the HTTP response code for each request, allowing a query to filter for 5xx server errors and identify which requests failed. Request_metadata stores contextual attribution information about the request's origin, including the calling application and other client-supplied metadata, enabling usage to be broken down by team or application. Sampling_fraction is a single configuration value that records the fraction of requests being logged for the entire endpoint, not a per-request measurement, and cannot be used to characterize individual request duration or origin. Databricks_request_i.d is a unique identifier assigned by the Databricks platform to each request for internal correlation purposes. It does not contain application identity information. Timestamp_ms records when each request arrived, which supports time series analysis but cannot be used to compute processing duration or identify the originating application. Let's pause here. Knowing what each inference table column actually does is worth your time. Imagine you're debugging a slow Friday deployment. Your model serving endpoint has an inference table, a log of every request. 3 specific columns solve this question's 3 requirements. Execution_time_ms records how long each request took in milliseconds. Average execution_time_ms gives you average duration, full stop. Status_code captures the HTTP code per request. Filter where status_code greater than equals 500 to find server errors. Request_metadata is a key value map holding endpoint name and model version, so you can group usage by configuration. The traps. Sampling_fraction is one config value for the whole endpoint, not a per request measurement. Databricks_request_i.d is just a unique ID. It tells you nothing about timing or origin. Timestamp_ms records when a request arrived, not how long it ran. Know the job each column does, not just its name. Here we go. Question 10. Read this one twice. A generative AI engineer at a datum configured an inference table for a production model serving endpoint to capture all request and response payloads. A colleague later altered the inference table by adding a new column intended to store custom routing metadata. The team subsequently notices that no new entries are appearing in the table. What is the most likely cause of this behavior? Select 1. Review the answer choices on screen. The correct answer is option C. Schema changes silently kill logging, no restart fixes it. Inference tables stop capturing request and response data when the underlying table schema is modified, when the table is renamed, or when the table is deleted. The schema change introduced by adding a new column is sufficient to break the logging pipeline, and no new entries will appear until the issue is resolved by configuring a properly structured new inference table. The 10 MB payload limit applies to individual oversized payloads and affects only those specific requests, not all logging activity. There is no manual restart mechanism that resumes inference table logging after a schema change. Databricks does not implement a read-only mode triggered by schema changes that requires acknowledgement in endpoint settings. Let's slow down here. This inference table behavior is subtle and shows up on the exam. Imagine you set up a security camera that logs everything to a notebook. Now someone adds a new column to that notebook. The camera doesn't know which column to write to anymore, so it stops writing entirely. That's exactly what inference tables do. An inference table is Databricks' built-in log of every request and response hitting your model endpoint. Once you modify that table's schema, add a column, rename it, delete it, logging stops cold. No error, no warning, just silence. The 10 MB limit? That only drops oversized individual payloads, not everything. A restart won't fix it either. You need a fresh, correctly structured inference table to resume logging. That's the trap. The schema change looks harmless, but it kills the whole pipeline. Storage optimized appeared twice more. The exam leans hard on billion vector scale. The reserved _i.d column name and the schema change logging failure are precise gotchas that reward specific Databricks knowledge over general intuition. Next up, question 11. The trap is partial correctness. A generative AI engineer at Western Fitness is building a personalized workout recommendation chatbot. At inference time, the system must combine two types of data: pre-computed user fitness history scores stored in an online feature store, and a dynamically calculated metric that multiplies the user's current weekly session count by a recency weight. The engineer is defining a feature spec to support this design. Which two components should be included? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Watch for invented feature spec component names in the options. Feature lookup retrieves pre-materialized feature values from an online feature store using a lookup key, making it the correct component for accessing the already computed fitness history scores at inference time. Feature function applies a user-defined transformation on demand during serving, which is the correct component for computing the dynamic recency-weighted metric that cannot be pre-materialized because it depends on the current session count. Feature index is not a component of feature spec. AI search vector stores are queried through separate retrieval mechanisms. Feature sync is not a feature spec component. Table publishing to the online store is a separate pipeline step performed before serving begins. Feature logger is not a feature spec component. Inference logging is handled through inference tables configured on the model serving endpoint, not within the feature spec definition. Next up, question 12. Let the constraints drive the choice. A generative AI engineer at Pelham Legal is building a RAG system over millions of commercial contracts. Queries must return the most precisely relevant individual clauses, but the context passed to the LLM must include several surrounding paragraphs to ensure accurate clause interpretation. Which chunking approach satisfies both requirements simultaneously? Select 1. Review the answer choices on screen. The correct answer is option C. Small chunks find the clause, the parent delivers the context. Parent-child retrieval separates search granularity from context granularity. Small 512 token chunks enable precise semantic matching during retrieval, so the system identifies the exact clause being queried. Once the relevant chunk is matched, the corresponding larger parent segment of approximately 2048 tokens is returned, providing the LLM sufficient surrounding context to interpret the clause accurately without truncating critical paragraphs. Fixed-size 1024 token chunks attempt to serve both purposes simultaneously and inevitably compromise on both, too large for precise clause-level matching and still too small to capture the full interpretive context for complex contract language. Semantic chunking groups text by topic coherence and produces clean semantic units, but without a parent-child relationship, there is no mechanism to expand the retrieval window after a small chunk match. Using zero overlap with recursive splitting increases the risk that clause boundaries fall between adjacent chunks, making critical text invisible to the retriever when a clause spans a chunk boundary. Next up, here comes question 13. A generative AI engineer at Thorngate AI completes training a large multimodal model and attempts to log the resulting checkpoint file, which is 7.2 gigabytes, to an MLflow run using mlflow.log_artifact. The upload fails with an error. What is the most likely cause, and what corrective action should the engineer take? Select 1. Review the answer choices on screen. The correct answer is option A. Over 5 gigabytes, log a reference URI, not the file. MLflow enforces a 5 gigabyte size limit per artifact file for both uploads and downloads. A 7.2 gigabytes checkpoint exceeds this limit, causing the log_artifact call to fail. The recommended corrective action is to write the large file to a supported external location, such as Unity Catalog Volumes or Amazon S3, and then record a reference to that location within the MLflow run, so the artifact remains discoverable. Using mlflow.log_artifact for binary checkpoint files is a valid and common pattern. The error is not caused by an incompatibility between the API and checkpoint file types. File format is not a contributing factor, as DBFS and Unity Catalog Volumes accept arbitrary binary content. There is no GPU accelerated transfer configuration in MLflow or Databricks cluster settings that affects artifact upload size limits. Let us keep moving. Question 14. Keep the constraints in view. A generative AI engineer at Meridian News is designing a vector search system for a global news archive containing over 1.5 billion article embeddings at 1024 dimensions. The current standard AI search endpoint handles queries correctly, but indexing new articles takes far too long to keep pace with the daily ingest volume. The team can accept an additional 250 milliseconds of query latency. What should the engineer do? Select 1. Review the answer choices on screen. The correct answer is option B. Slow indexing and a capacity ceiling are the same root problem. Storage-optimized AI search endpoints are purpose-built for corpora exceeding 1 billion vectors and provide 10 to 20 times faster indexing compared to standard endpoints, directly resolving the ingest throughput bottleneck. The known trade-off is approximately 250 milliseconds of additional query latency, which the team has explicitly accepted. Standard endpoints handle approximately 320 million vectors at 768 dimensions. Distributing across multiple standard endpoints avoids the root issue because each endpoint still has the same indexing throughput ceiling, and the architecture adds routing complexity without increasing aggregate capacity. Reducing embedding dimensions changes the semantic representation of all documents and requires re-embedding the entire 1.5 billion vector corpus, creating substantial rework without addressing the fundamental mismatch between corpus scale and endpoint type. Concurrent indexing thread counts are not a user configurable parameter on Databricks AI Search endpoints. Now, question 15. Read it carefully. A generative AI engineer at a healthcare company wants to understand which models and notebooks are consuming features from a specific patient demographics feature table before a planned schema change is applied. The team needs a complete dependency graph without requiring engineers to manually annotate their work. Which Databricks capability provides this visibility? Select one. Review the answer choices on screen. The correct answer is option C. Manual tagging does not scale. Automatic UC lineage does. Unity Catalog provides automatic feature governance and lineage tracking that records how feature tables are consumed by models, notebooks, jobs, and pipelines across the workspace. This gives the team a queryable, automatically maintained dependency graph that immediately surfaces every downstream consumer of the demographics table before the schema change is applied. MLflow experiment search with run tags requires engineers to manually tag every run with the feature tables they use, which is error-prone and does not scale across a large organization. AI search metadata filtering is for document retrieval, not for tracking feature consumption relationships. Model registry tags also require manual maintenance and do not produce the automated, workspace-wide dependency graph that lineage tracking delivers natively. Feature spec only accepts real SDK components. Feature index and feature logger are invented distractors. Unity Catalog lineage is fully automatic. MLflow's 5 GB per artifact ceiling forces large checkpoints to external storage. Time for another one. Question 16. Track every qualifier. A generative AI engineer at Meridian Healthcare is building an LLM-powered documentation assistant for clinical staff. The organization's compliance team requires that no patient personally identifiable information, including email addresses, social security numbers, and phone numbers, may be transmitted to or returned from the language model. The protection must be implemented at the infrastructure layer without requiring application code changes. Which AI gateway feature meets this requirement? Select one. Review the answer choices on screen. The correct answer is option C. Infrastructure layer and no-code changes point straight to AI Gateway. PII detection and redaction in AI Gateway automatically scans incoming requests and outgoing responses for personal identifiers such as email addresses, social security numbers, and phone numbers, replacing them with neutral placeholders before content reaches or leaves the language model. This operates at the infrastructure layer with no application code changes required. Safety filters are designed to block harmful content categories such as hate speech, violence, and sexual content. They do not identify or redact personal identifiers. Rate limiting controls request frequency and protects against cost overruns and SLA violations, but it has no mechanism to inspect or sanitize the data contents of requests. Traffic splitting routes requests between endpoints based on defined weights, but cannot inspect payload contents to detect or remove PII. Time for another one. Question 17. Wording first, memory second. A generative AI engineer at Summit Legal is evaluating the retrieval component of a RAG pipeline that answers regulatory compliance questions. Each user question has multiple known relevant documents, and the team needs to confirm that all known relevant documents appear somewhere in the top 10 results, regardless of their exact position in the ranking. Which retrieval metric best fits this requirement? Select one. Review the answer choices on screen. The correct answer is option C. Presence anywhere in the top K, regardless of position. That's recall. Recall at K measures the fraction of all known relevant documents that appear in the top K results, making it the correct metric when completeness is the priority, confirming that no relevant document was missed, regardless of where it appears in the ranking. NDCG at 10 is the strongest metric when both relevance quality and ranking order must be jointly measured, but it penalizes relevant documents found at lower positions rather than simply verifying their presence anywhere in the set. Precision at 10 measures what proportion of the retrieved results are relevant, which addresses quality of the retrieved set, but does not confirm whether every known relevant document was captured. NDCG at 10 rewards highly ranked documents with greater weight and captures relevance intensity on a 0 to 3 scale, but is designed to assess ranking quality rather than completeness of recall across the full set of relevant items. Ready? Question 18. Separate context from noise. A generative AI engineer at Orion Analytics is comparing two prompt templates for a knowledge base Q&A assistant. After independently scoring each template with an LLM as judge using the built-in 0 to 3 relevance scale, both templates receive average scores between 2.7 and 2.8, and the difference is not statistically meaningful. The engineer needs an evaluation method that will more reliably distinguish quality differences between the two templates. Which approach should they use? Select one. Review the answer choices on screen. The correct answer is option D. Score compression near the top of the scale hides real differences. Pairwise comparison is purpose-built for directly contrasting two candidate outputs. By presenting the query and both responses to the judge simultaneously and asking it to select the better one, this methodology captures relative quality differences and produces judgments that align more closely with human preference than independent scoring does. Single output scoring evaluates each response in isolation, which introduces inter-run variance and score compression near the top of the scale. When two templates produce similarly strong responses, aggregate averages often fail to discriminate between them reliably. Increasing the judge model's temperature introduces noise rather than signal, and does not fix the fundamental problem that pointwise scoring cannot capture relative quality between two high-performing candidates. Retrieval groundedness measures whether a response is supported by retrieved context, and is a RAG faithfulness metric, not a mechanism for comparing prompt template quality. G-Evil with chain of thought is a single output technique in which the judge reasons step by step before assigning a score to one response. It is not designed for head-to-head comparison of two candidates and shares the same instability drawbacks as other pointwise scoring methods. Let's pause on this one. Picking the right evil method is a classic exam trap worth understanding. Imagine you're a judge at a wine competition. You score two bottles separately. Both land at 93 points. The scores look identical. No winner. Now put both glasses in front of you and ask, which do you prefer? A winner almost always appears. That's pairwise comparison. It shows both responses to a judge model at the same time and asks it to choose. This breaks through score compression. When scores cluster at 2.7 and 2.8 on a 0 to 3 scale, they look identical. The side-by-side test cuts through that. Retrieval groundedness checks if a response is backed by source docs, a different job entirely. The question rewards knowing that head-to-head beats independent scoring when two templates are already strong. Ready? Question 19. Avoid the familiar but wrong answer. A generative AI engineer at Heliograph AI is building a semantic product matching system using Databricks AI Search. The embedding model they chose uses cosine similarity as its native metric, and after storing embeddings in the index, they notice the similarity scores do not reflect the angular distance between vectors. A colleague explains this is because AI Search applies a different internal distance function. What must the engineer do to their embeddings before storing them in the AI Search index to achieve cosine similarity behavior? Select one. Review the answer choices on screen. The correct answer is option D. No metric underscore type parameter exists. Normalization is the only path. Databricks AI Search uses L2, Euclidean, distance with the scoring formula 1. 1 plus squared underscore distance. Cosine similarity is mathematically equivalent to L2 distance when all vectors have been normalized to unit length, because normalizing removes magnitude from the equation and makes the Euclidean distance between two vectors proportional to the angle between them. Pre-normalizing embeddings before storage is therefore the required step to achieve cosine similarity behavior without any additional index configuration. There is no metric underscore type configuration option available for AI search indexes. L2 is the only supported built-in distance function, and it cannot be overridden at index creation time. Sparse vectors are used for keyword-based BM25 search, not for controlling which geometric distance formula is applied to dense embeddings. Increasing embedding dimension changes the model's representational capacity, but has no bearing on which distance metric the index applies during retrieval. Let's slow down here. The AI search distance function is a common exam trap worth nailing. Imagine storing 1,000 product embeddings, then seeing red dress rank closer to bicycle helmet than blue dress. That's the L2 trap. Databricks AI Search uses only one distance function, L2, straight line Euclidean distance. Your model was trained for cosine similarity. Those two give different rankings unless you fix one thing. When every vector has length exactly 1.0, L2 and cosine give the same ranking. The fix: divide each raw vector by its magnitude. That normalizes it to unit length. Then store that normalized vector in the index. There's no metric underscore type setting in AI search. Option C doesn't exist. The question rewards normalizing the data, not configuring the index. Let us switch gears. Question 20. One answer is too broad. A generative AI engineer is building a semantic search system, and their team's benchmarking shows that cosine similarity consistently outperforms the default distance metric for their document corpus. Databricks AI Search does not expose a native cosine similarity parameter. How should the engineer configure the system to achieve cosine similarity behavior? Select one. Review the answer choices on screen. The correct answer is option B. Unit length vectors make L2 and cosine rankings identical. Databricks AI Search uses L2, Euclidean, distance with the HNSW algorithm and does not expose a native cosine similarity parameter. When all embeddings are normalized to unit length before indexing and before each query, L2 distance and cosine similarity produce identical ranking results, because the magnitude component cancels out. Pre-normalizing is therefore the correct and only supported way to achieve cosine similarity behavior. There is no distance underscore metric parameter accepting cosine in the AI Search Index Creation API. Storage-optimized endpoints use the same HNSW algorithm with L2 distance as standard endpoints and do not switch to cosine similarity. Direct access indexes allow callers to supply their own embeddings, but do not introduce a cosine similarity configuration option. 3 takeaways from this session. First, storage-optimized AI search unlocks billion vector corpora, with 10 to 20 times faster indexing at a known 250 millisecond latency cost second. Parent-child RAG decouples retrieval granularity from generation context, solving precision and completeness simultaneously in one index. Third, Unity Catalog provides automatic feature to model lineage with no manual tagging, making it the single governance source of truth for ML assets. Every question in this set mirrors a real architecture decision: storage limits, retrieval precision, governance scope. You have just pressure tested your instincts on the patterns that matter. Keep building that edge.